Good evening, everyone. I would like to welcome you all to the Nobel Talks, and now I'll pass the word to Filipe.
Can you hear me?
Yes.
Okay. So good afternoon, everyone, and welcome to this Nobel Talk. My name is Filipe, and I'm a student at the University of Técnico, and I'm representing the students' units of the same university that is organizing these events in collaboration with the PhD Student Club. First of all, thank you everyone for being here today. This is the World Engineering Day, and we have here a unique opportunity to hear from the Professor Michel Mayor, which is 2019 Nobel Prize laureate in physics. I would like to thank Professor Mayor to accept to be here and speak with us. This will be a great opportunity for all the students that are here to learn and sharpen their curiosity and to meet such a Nobel Prize winner like you. As I said, this is done in collaboration with the PhD Student Club. So to moderate this session, we have here Gabriel Cristinol, who is a physics student at Técnico, and Fábio Cruz, a recent Técnico PhD graduate in physics and now researcher at Inductive Research Labs. I'm going to pass my word to them. They will introduce our guests.
Okay, thank you, Filipe, and welcome everyone once again to this event. Before moving on to our guests' talk and an interview, I'd like to invite everyone to write down your questions or raise your Zoom hand, and at the end we will read these questions out loud or ask you to unmute and speak up and ask your question. So our guests for this Nobel talk, very honored to have him, is Michel Mayor, Swiss astrophysicist, who is an emeritus professor at the University of Geneva and also a researcher at the Observatory of Geneva. Apart from other many distinctions in his career, Professor Mayor shared the 2019 Nobel Prize in Physics, like a few people were saying, with Professor Jim Peebles from Princeton and Professor Didier Queloz from Cambridge University, and shared the prize for the discovery of the first exoplanet orbiting a solar type star. So today, like I said, we're very thrilled to have the chance to host Professor Mayor for a talk and an interview about his academic and scientific career. So thank you once again, Professor, for accepting our invitation, and please start when you're ready.
Thank you.
So, Professor, would like to start by maybe asking you if you could describe a bit how was the beginning of your career? How did you start, your career as a scientist, and how did your interest for science started?
Yes. So hello, hello, everybody. I'm very glad to discuss with you. It will not be formal. It's just few sentences. When I was a kid, I was quite interested in science, not specifically in astrophysics. But when I was a teenager, I started to be more and more attracted by theory. So I did my study in theoretical physics. My master was devoted to interaction of particles with large spin, absolutely not in astrophysics. And then after I did a PhD, also devoted to a theoretical domain, it was a problem of the what is called density wave in galaxies. You know that you have certainly seen this beautiful picture of a galaxy where you have two big spiral arms. So the dimension of these arms is something like 100,000 light years. It's so huge. It's huge. What is a physical process to explain the shape of this structure? So this was proposed in the 60s by two Chinese physicists, and this has opened quite a lot of questions. And I did my PhD in this domain. And this theoretical explanation was looking for maybe what we can find as a test of in the local vicinity of the solar system. Do we have the possibility to to add few tests to see, for example, if the mean motion of stars is perturbed by the density wave. So it was the reason why this was the start of the discovery of planets. It's not evident because when I finished my PhD, just to do this kind of test, I need velocity of stars to see if the global flux of stars was perturbed by the density wave. And at the time, it was awfully boring to measure velocities of stars. And by chance, I was attending a conference in Cambridge in the 70s, and I met English astronomer testing a new techniques to measure what is called cross-correlation. You do some kind of negative of the typical spectrum of a star, you project the spectrum of the star on this grid, and then after you can try to see the correlation between two to measure the velocity of the star. With this kind of device, you can concentrate all the Doppler information stored in the spectrum in one quantity, only the velocity. It's so efficient, so huge. So I was really attracted by this technique. And it's at the time I decided to change my career and start to do some instrumentation. So I've developed some kind of more precise spectrograph, cross-correlation spectrograph in Geneva. It was something like more than 1,000 times more efficient than the old technique of photographic plates. And it was easy. It was during 15 years, I really enjoyed to do a lot of different things. Dynamics of globular clusters and so on, studying double stars, because maybe you know that most of the stars are stored in double stars or triple stars. So quite a lot of different things. And my first spectrometer was built in the 70s. It was Coravel. It was observing in Chile and south of France. We have two instruments. And 15 years after, the director of the French observatory south of France asked the opticians and myself if we would like to develop a new instrument for a larger telescope and with modern technology. And evidently we are quite attracted for that. And we have developed a new spectrograph called LOD, with some taking advantage of the progress of the technology. And when we did the very first test in the dome, we realized that the precision was something like between 10 and 15 meters per second. So it was just what we need to detect planets. So immediately we decided to change our program and not to do galactic dynamics or cluster dynamics, but just to use this instrument to search for planets. And evidently this is a very short summary, because when you want to build an instrument, you need a lot of money, you need a lot of people, because it's not a one body only to do this development. You have a lot, maybe 10, 12 people, to engineers and so on, to develop this instrument. And I asked the observing time at the French committee, and we receive 1 week of telescope every 2 months. At the time, it was considered to be a very large program, but in fact, it's not so much. It's you have 7 days. Sometimes you have rain or clouds, and then after it, you have to wait two months before the next measurements. Nevertheless, we start this program with 2 of my students. One was Antoine Duquesnoy. He was a postdoc, and the other one was Didier Queloz. He was the youngest. At the time, he did not have any PhD. It was just finishing physics study. And we start the program measuring a selection of something like 140 solar type stars similar to our sun. And it was very rapid. Very soon we discovered an object where the velocity was changing, because the trick of this technique was not to search, to look for planet, but just to see the indirect detection. You are measuring the velocity of the star, and you see that the star is changing of velocity. And if you have a periodic change of the velocity, this is due to some physical process. And if after a few very simple calculations, you can determine the mass, period, and so on, eccentricity of the orbit of the object perturbing the star. And the theory at the time was that we cannot form a giant planet with a period shorter than 10 years. And the surprise was the object we have detected was with a period of only 4.2 days. So it was a discrepancy with the theory by a factor 1,000. So, okay, you have to be a little bit careful when you have a discrepancy so large. The domain of the detection of a planet was known to have a lot of false detection. So it was a good reason to be extremely careful before announcing this discovery. So we have decided to wait one additional year, and in July 95, we have remeasured the star, the velocity of that star, 51 Pegasi, and we have recovered exactly the same shape, same period, same amplitude, same phase. So we have been convinced that it was due to a companion and not to pulsation or magnetic activity or things like that. So this was the start of the story. And immediately after the announcement, it was a completely crazy time, because we were not prepared for that, because all big journals in the US and in Europe ask comments and so on. And we say, okay, this is a matter of 1 or 2 months, and then after we can continue like before. But not 25 years after, it was still the same case. We have a lot of pressure of people. And this is directly an answer to one of your questions. What is the impact for the general public on the daily lives of this discovery? I believe we have to go back in the past. In fact, for more than 2,000 years, people was asking, do we have other worlds in the universe? Do we have life in other places in the universe? So this was always present in the discovery, in the discussion of philosophers, scientists, and so on. So evidently, for most of the people in the street, they are evidently not thinking every day to this kind of question. But when we consider the huge amount of questions, of asking for conference, asking for, so this is really, I believe, a big concern for people. So this is good to see this. And I believe it's nice to see that people are not only looking on the ground, but sometimes looking in directions of the sky. So, and from the time we have continued this kind of story of adventure. For example, the first spectrograph, something 50 years ago, was a precision of 300 meters per second. This typically visible velocity of a jet. Then LOD, having allowed the discovery of 51 peg, was 13 meters per second. It's a bike or something like this. And after we have developed a new spectrograph, ARPS, In 2003, it was 1 meter per second. So this is the velocity of a lineman. And then after the last spectrograph in this series, espresso, developed with people from Lisbon also and Porto, the precision is something like 0.1, 0.2 meters per second. Let's imagine you see a star at some dozen of light years, and you detect change of the velocity of 10 centimeters per second, and with a period of something might be 1 year. So this is typical of the difficulty of these things. The technology behind this interesting question is absolutely present. The discovery of the exoplanet is really due to the progress of technology.
Yeah, wonderful. I want to come back to something you said when you were describing the relevance of this discovery. So this search for extraterrestrial life kind of intensified with your discovery. And so I wanted to ask you, in your point of view, what does the path to find that extraterrestrial life look like? So what instrumentation are we still missing? How long it's going to take us to do that until we find it?
Yes, this is typically what is the most interesting for all people, because for astrophysicists, maybe you are already very interested in the formation mechanism, the physical process for the formation of the solar system or any planets. But evidently, for most of the people, the basic question, do we have the capability to detect life on some of these planets? And this is very strange, because still today, we cannot observe the planet, except very big one at large distance of stars, but most of the time, we do not have the possibility to see this exoplanet. And we're asking, is it possible to detect life on this planet? And it looks completely crazy to ask this kind of question. And I will try to describe the idea. As we have detected quite a lot of planets with relatively short period, so this corresponds to relatively short distance between star and planet. So time to time, you have the possibility to observe transit, planetary transit. Planetary transit is some kind of eclipse. And when you observe and you compare the spectra of this of the star, when the planet is in front of the star or behind the star, and you compare the two spectra, you have a small difference due to the fact that the atmosphere of the planet filters the light coming from the star. So you can have access, the difference of two big numbers, the spectrum, the two spectra, you have a very small difference due to the atmosphere of the planet. And if you analyze the chemistry, the spectrum of this planet, you have the possibility to detect the composition of the planet. You cannot see the planet, but you have access to the spectrum, and you can have access to the chemical composition. And if you have the good science, the good life, the good study for the life process, maybe you can dream to detect what is called biomarker. Biomarker is change in the atmospheric composition due to the development of life. The typical example given in this domain is the fact that the atmosphere of the Earth has something like 20% of oxygen. 20% of oxygen, we learn this in the school, and okay, this is important for life development, but nobody realized that it's absolutely exceptional, because one characteristic of oxygen is to do some chemical link with rocks to form oxides and so on, and to decrease very sharply. And so if we need a process to maintain the oxygen level at 20%, we have to, the most evident one is a process related with life development. So this is not absolutely sure because we can find some different alternative. So you need to combine the detection of different chemical composition. But it's only via the analysis of the chemical composition of the atmosphere of planet, transiting planet, that we have a chance to detect some form of life. But it's very interesting because at the present time, you have a huge effort in some institute or network of institute, including astronomers, biologists, geophysicists, chemists, theoretical physicists, and so on, because the problem of life is absolutely not easy. Because, okay, we have one example of life, is the life we have on the Earth, but we are absolutely not sure that's the only possibility. So at the present time, the Center of Bioastronomy are extremely, I would say, exciting domain of science to try to analyze what is life. Life exists in other place. What is the origin of life on the Earth, and so on. So it's a very big domain of science of today.
Thank you so much, Professor. That's an incredibly interesting point.
Maybe I can add, we still not have exactly the good instrument, because we have done this kind of detection of chemical composition of planet, but it was mostly giant planet. Because giant planets have a relatively large atmosphere, so we have a not negligible effect. But when you are looking at a rocky planet with relatively small size, in fact, the influence of the atmosphere is very, very small. So at the present time, we still not have the capability to do it. And still, for example, the James Webb telescope launched last December will still not have the capability to really measure the Earth, the rocky planet of the mass of the Earth. Probably it will succeed to do for little larger planet, maybe with a mass of 2 or 3 times the mass of the Earth, but this is just at the limit of the technology. So it's, I believe, I'm not sure that we will have some answer to this huge question, do we have life in other parts of the universe next year or something? We need to develop instrument, have long exposure time, maybe from the ground, because we can do also this kind of study from the ground. And you know that Europe is developing a telescope of 39 meters of diameter in the north of Chile, in the Atacama Desert. So what is important is that when you look for the small difference between 2 big numbers, the spectrum of the star, when the planet is in front or behind, you have a huge number, and you are looking just for small difference. You need a lot of photons. So maybe we can dream that this kind of giant telescope coming soon, a few years, will help to answer this big question. Sorry.
No, thank you so much. Our next question is actually a bit related to that, because as we know, research can be full of obstacles and failures. So we were wondering if you could tell us about one of those struggles you went through, maybe in the path that led you to the Nobel Prize.
Yes, difficult question. For example, I was a theoretician. So when I was starting to discuss with the director of the Geneva Observatory in 71, I believe, if I remember correctly, I said, I would like to develop a spectrograph by cross-correlation. What is the reaction of the director? He was laughing because it was not typical of what a theoretician asked to do. So moving from theory to observation instrumentation was quite surprising. finally, and then after you have to find the money. It was the Swiss National Foundation, money and so on. So, okay, and people, because I was not alone, you have engineers and so on. And then 15 years later, when the director of the French Observatory Haute-Provence asked to develop the second generation, more precise, we have exactly the same path. So we asked the money to the French committee, and the money was refused. So people was not convinced at all by the interest of this thing. So you see, at the present time, everybody say, okay, it was a good idea to do it. But in 1998, at the end of 80s, it was quite difficult to convince people that we will be able to measure velocities at such a precision. So this is part of the difficulty. And then, evidently, when you are developing an instrument, always you have some difficulties, you have problems. I would just mention one or two examples. One, we have a big collimator, a big mirror in the spectrograph ARPS in Chile. And we were under pressure because we received observing time in February 94, February 2003, and you have to be ready in time with this very complex instrument. And we received the collimator, this mirror, and it was error. It was not correct. I will not describe what was the errors, but the surface includes some periodic defect. So we have been obliged to find a new industry to correct the defect in a very short time and to send this mirror to be ready in time on the telescope in La Silla in Chile. So you see, you are touching real matter, and you have deadline because the telescope is heavily requested by people. So in 1 year in advance, you will have time in February 94 and so on. Voilà. This is some of the typical difficulties on the process, and evidently you have also difficulties. For example, I mentioned with the first spectrograph, no, the second LODE, we were starting the program at 3. You have Antoine Duquesnoy, who was a postdoc, he was part of the team, and he died in a car accident during the first observing period. So you see that, okay, this is part of the life when you have a complex instrument, and it's not a big industry with a lot of people doing the same thing. So you have some single failure point. So when you have one people able to do something, so okay.
Thank you so much. That's very impressive to see how that works. Now we're gonna take a question from the audience, and Pedro asks something related to one of your answers before. The biomarkers you mentioned, aren't they restricted only to forms of life similar to the ones we know?
Yeah, this is part of the difficulty. Nevertheless, you have some constraint. You cannot do what you want. We do not have the choice to abandon the carbon, because the chemistry based on the carbon allow very complex molecules. Okay, some people try to see if we can find an alternative, but in fact, in the nature, we do not have a very complex chemistry based on the different atoms. So you have atom, you need to have the chemistry, and you have to transfer. Okay, this is a basic definition of life. I don't know if it's definition, but it's a characteristic of life. The fact that you need to transfer the information. Because when you have a very single form of life, you need to protect with this small machinery from their surrounding. you need to exchange energy and component matter with the surrounding. But one of the most important characteristics of life also is that you need to transfer all this information to your daughter. And this is probably one of the most important characteristics, what we call life, this capability to transfer the information from one generation to another one. So up to now, the only way we have is DNA. It's a long chain of atoms and coding all the information to life, to function. And okay, people can dream to invent different techniques. This was a typical game 40 years ago to find different alternatives to this kind of way to transform information. But up to now, it's the only way we know. So if you eat too much, this long chain of atoms, it will be destroyed. And typically we can discuss it's 120 degrees. You have some, maybe some possibility to have a little bit higher, but it's typically 120, 150 degrees. If you are at the opposite, at very low temperature, chemistry is so low, nothing very interesting happens. So you are limited to a domain typically close to the domain of liquid water. In addition, water is an absolutely fantastic possibility to I don't know the name, to facilitate the chemical reaction. So you need to search for planet with the ground, with the domain of temperature. Then after, we do not know. And at the present time, you have fascinating studies to try to see if we can find alternative form of DNA in different bacteria on the Earth and things like this. And it will be a dream we can have. Let's imagine we find some form of life in the ocean below the ice shield of Europa. Europa is one big satellite of Jupiter. At the surface, you have an ice shield, but you have an ocean below. The water is maintained in liquid form due to the tidal interaction of the different satellites. So if life, let's imagine that we have some kind of elementary form of life under the ice shield of Europa. Are we sure that it will be exactly the same DNA or not? Is it a completely different form and so on? So this is a completely new domain of science and is probably much closer to biology, fundamental biology and things like this. So, and at the present time, the bioastronomy and exoplanet research concern a lot of people.
Yeah, well, lots of interesting questions for the present and future generation of physicists, chemists, and biologists. So quite interesting. I wanted to come back to the research that led to the Nobel Prize that you were recognized with. So I think you were one of the very rare cases where you were awarded this prize with one of your PhD students at that time. With the Didier, right? So my question is if you could describe a bit how was your relationship back then and what was the relevance of this interaction with your student for the success of that research program?
Oh, it's very natural things. In fact, Didier was one of my students, undergraduate student, and I gave him, he asked me to do a master with me, and the topics of the master was, okay, I will try to explain a little bit. When you are doing the cross correlation of the spectrum, so the position of the cross correlation fraction gives the velocity. if the star is rotating, you have some atom moving in your direction, the other ones receding. So you have access to the velocity, rotational velocity of the star. If you have a lot of heavy elements, the correlation function will be larger. So you have some kind of indication of the chemical composition of the star, and so on. So I asked Didier to explore the possibility to determine other parameters like the gravity in the atmosphere or magnetic field and things like this. And he did this for the master. And after, it was just the moment we have finished the definition of the spectrograph with André Baran, engineer of optics of Marseille. And we need to recruit, to hire people in different fields. And Didier was just starting his PhD at the time, and he need to have a spectrograph to apply what he was developing. So I asked him, do you want to collaborate with this project? And this specifically to extract the signal of the CCD to measure after the velocity. It's not simple because you have a lot of tricks, you have cosmic rays and so on and so on. And this is the reason why Didier started entering it. It was, his PhD was absolutely not devoted to search for planet, because it would have been crazy to give topics like this when you have no idea at all. Because the only things we have that if we have a planet, it should have a period larger than 10 years. So it was evidently not a PhD topics. And so he started to do the software, part of the software of this instrument. And he was quite involved in this technique. He was really enjoying this kind of development. So when we have decided to ask observing time to search for planet, it was a natural comportment behavior to continue together. And so it was the reason why he did his PhD after the discovery of 51 peg. And then after we continued to work together during several years. He moved for 1 year, I believe, in the States, in US. He went back in Geneva, and we have been working because the domain was so exciting at the time. Because just to have an idea, okay, 95 in July, in summer 95, okay, we start to have the discovery of 51 peg. But in January 96, the American Butler and Marcy discovered 2 planets, one with a period of something 100 days, and another one with 1,000 days, because they have old material not analyzed before. So immediately we say, if you have several, okay, we were extremely stimulated to increase the observation, and we have doubled the request for observing nights. We receive 1 week every month for that, and the number of detection increased immediately, and today we have 5,000 planets detected. So it's evident for Didier, it was a perfect subject, and we have abandoned all our old domain, and Didier never studied what was supposed to be his PhD.
Which turned out nicely for him.
Yes.
Right? Okay. So related to this, I think I read in one of your previous interviews that one of or the most important characteristic of a scientist is just curiosity, just natural curiosity. So my question is now how you do that yourself, how you keep curious, but how do you try to keep your team and your students curious?
I believe it's simply natural. I believe we have okay. The team at the beginning we were only a few, but at the present time we have 40 people, a lot of different domain of exoplanet, and we have a lot of excitation because it's a new domain. You have a lot of new questions. As it's a new field, it's very easy to have ideas. Okay, the physics is not easy. It's much more complicated than 40 years ago. And the physics made by my young colleague right now are certainly much more complex than what we did many years ago. And for example, one typical example is the fact that, okay, we have developed very precise spectrograph. And maybe with the velocity, the precision of the spectrum is around 0.1 meter per second. But the real difficulty is the fact that the noise is not coming from the spectrograph, but right now is coming from the star, because the stars have a magnetic activity, and we have a lot of physical process. You have acoustic mode in the atmosphere, you have spot, you have eruption, you have convection, and so on. All these processes have, in the very best case, at least the jitter, the fluctuation of the velocity due to the magnetic activity, is at least 1 meter per second, maybe more. So it's much bigger than the effect that you are looking for. So at the present time, young people are trying to develop very clever way to turn around this difficulty, to select line, to have software kind of treatment of the signal, to try to measure this very teeny phenomena. Just to have an idea, you have the spectrograph, you have the CCD, you have the spectra projected on the CCD, you have some absorption line. Absorption line have typically, at best, 1 meter, equivalent of 1 or 3,000 meters per second. So we are measuring something like 1,000 times smaller than the width of one very thin atmospheric line. So, and it's few silicium atoms on the CCD. So it's really very, and it's not a place to discuss these things, but you have a lot of very small effect to be corrected. And the general relativity relativity and so on, you have a lot of things to try to eliminate, to have this, to maintain this precision.
Thank you so much. It does seem like there's an infinity of things to explore in this domain. Our next questions, yeah.
No.
Okay. Our next questions are a bit more related, something you might get a lot, which is Nobel questions. But the first one is, could you describe the moment in which you got the call from the Nobel Committee?
I knew from the very first years that Didier and myself were nominated. So it just proposed. And at the time, one member of the committee said, no, your problem is to get old. Because maybe you know the difference, the time difference between the moment of the discovery and the moment maybe you receive the Nobel Prize is something like 30 years. So, okay, so I succeed to get old enough. And then after, okay, we knew that the Nobel Prize are given during the first week of October, are announced in the first week of October. But I've decided with my family to completely ignore this fact. We took vacations, we took up some, and because if you are every year, okay, what will be the decision? It will be crazy. So I completely ignore this. I knew that sometimes we have been on the short list and so on. It's not a problem. You have no way to act. And for example, in 1919, I was doing babysitting in Spain because I have grandchildren, and the father and mother was invited to a wedding party in San Sebastian in Spain. They asked us, you will take care of the two small boys, 3 and 5, or 2 and 5, 2 and 4 at the time. And so we did this in San Sebastian. And at the time, I did not have any mobile phone. So I didn't receive any first announcement of that. And just before leaving the flat where we were in San Sebastian to go to the airport to go back, I say, oh, I can see my mail and so on. And it was just at the time I received the message that they announced this in Stockholm. But it was the time to take the bus to go to the airport. So I have not seen the end of the announcement. And then it's only after that I received a telephone call with the mobile of my wife at the airport to discuss a little bit with the people in Stockholm. So
might have been a bit chaotic for the committee itself.
No, I knew that some colleagues, having done very important things, was always too much concern with if they can receive the Nobel Prize. I believe it's completely a bad way to live, because you see that when I was in Stockholm, I discussed with some people from the committee, and I asked the question, how many people are nominated year after year in physics, in chemistry, in medicine? Always more than 300. So every year you have 300 people having done superb things, I'm sure, in physics or in chemistry or in medicine. And so you see, you cannot planify. You have to be lucky, I don't know. You have the problem of the impact. Well, you have a huge number of absolutely fantastic things made in science, but some of them do not have, for some reasons, an immediate impact. So, and it's evident the domain of exoplanet had a very large impact. You see that you have, I don't know how many thousand people working in that field right now.
Thank you. Our next question is a bit related to that, to the impact that these things have on your daily life. How has your life changed since receiving the Nobel? Do you still do research, or is it just conferences every day?
I will give you another. Do not accept any to receive a Nobel Prize. No, because the pressure is terrific. You cannot imagine the number of emails I receive. It's completely crazy. And then after you receive invitation to go to give a lecture or something like this in India, or in China, and so on. And so evidently at the beginning, you are very glad. You are okay to have the opportunity. But when you have, I don't know, 20, 30, 40 invitations to go in different places, and you realize it's no more popular. And we have been a little bit happy because the COVID just arrived in March 2020 and slowed down immediately this completely crazy period. But eventually the Zoom period start. And okay, and so no, I'm not complaining. I'm joking a little bit, but it's evident. But I have not discussed so much with my colleague having received the Nobel Prize in medicine or in chemistry right now, if they suffered exactly the same pressure, or if this is related to the topics of exoplanet. Because evidently exoplanet is something very easy to discuss with people. So maybe some domain of science are not so immediate to discuss and to I would say to give lectures for the public. Next time I will ask if I met some of my people, colleagues having received the Nobel Prize in 19, if they are suffering exactly the same. I don't know.
Maybe I'll just ask one last question from the public. Miguel asks, what are other methods besides spectroscopy which you believe will allow us to make new discoveries in the field of bioastronomy? Not sure if
So
you have any idea.
the first technique was Doppler spectroscopy. The second one, having given huge amount of results, was a transiting planet. And you have, for example, Kepler, TESS, a lot of different satellites, space mission, have revealed a huge amount of planetary system, some of them with 6, 7 planets, and so on. So this is, okay, existing. You have a different techniques. You have, for example, what is called microlensing. Microlensing it's a consequence of the general relativity of Einstein. You have the bending of the light going close to a mass. So if you have very distant stars and almost line with a star, a closer star, you have the possibility to have something equivalent to a focusing of the light. So suddenly you have an increase of the luminosity of the star, and this is what is called microlensing effect. If you have a planet close to the star, you can have a more complex increase of the luminosity, and you can detect planets at relatively large distance of the stars. Some of them may be with very small mass. You need a very perfect alignment, but you have the possibility to detect very low. So this is interesting for the statistic, because you can use it to explore long distance planets. But you cannot repeat the measurements. So for me, it's not so exciting. For me, the last 20 years was really the period of the discoveries of the planetary system. And right now you have a fantastic period where people are doing spectroscopy, biomarker, analysis, physics of the atmosphere of planets. So this is absolutely fantastic. And you have the Gaia satellite launched by ESA recently, and they're measuring the position of stars. So if you have a planet hosted by this star, in fact, the position of the star will be oscillating. We have a small wobble, not in the velocity, but in position of the sky. And so you have the possibility to detect planet by astrometry. Okay, I believe this will be, the first planet will be announced in a couple of months. So I don't know how many, but I'm sure there, and this will be the first planet detected by this technique. So this is typically for me, I believe the spectroscopy is really the most exciting domain. And maybe study on the Earth. You have people studying exotic small form of life, and looking if the DNA is changing one place to another one, and space research. If we can find some form of life in the ocean under the ice field of Europa, or maybe in the you have other planet, you have other satellite with geyser, and for example, Enceladus have a geyser, and you have some space mission planned to analyze the chemical composition of these geysers and to look if you have some form of life inside, and so on. It's completely crazy, because when I did my study, I don't know, a long time ago, nobody discussed the possibility that we can have life outside the Earth. And right now you have the possibility, Mars, old form, Enceladus, Europa. So you have several places maybe where you can have some extremely simple form of life.
Thank you so much. One last question, actually. While on this topic of new space exploration, Andre asks about the James Webb Telescope, if there's anything you're most excited about.
Yes, biomarker. So, what kind of level of precision we can achieve with the analysis of the chemical composition, and for example, you know that you have a few very close stars with planet, orbiting planet. One is Proxima du Centaur. It's the closest of all, and with a planet in the habitable zone. No, not in the habitable zone, but relatively close. And the other one is TRAPPIST-1. It's the name of the system, with 7 planets, 3 of them in the habitable zone. And this will be, I would say, top priority object to be analyzed, measured by the Space Telescope. So I don't know, we will see. But always you have to keep in mind that the most exciting things are not right now expected. So, you know, if you are going back to what was the arguments given to the US government to give the money to build the Hale telescope, the 5-meter telescope at Palomar. None was really interesting. It was absolutely not what was the most interesting thing. It's only after that we see what was interesting. So maybe we can dream that we will have a good surprise. And I'm sorry, but you see that you can have the Nobel Prize if you are very badly speaking English.
No, your English is great.
Sorry.
That's not the case at all. And we'd like to thank you so much for taking the time out of your surely busy schedule to talk with us.
Merci.
I'm sure a lot of physics students are very excited to go find out what these new things are that we're going to get excited in 10 years. And I don't think there's any more questions, so I'll go to Filipa to close the session.
I would say just a general comment. Science is fantastic. It's really a different domain of science. You can do archaeology, you can do medicine, you can do studies the brain and so on. So fantastic domain. Maybe you will not be very rich, but it's nice. Okay, bye-bye.
Bye, thank you.